Okay, so probably some words before I start. So far, let's close the door. So far, we've seen Maurer-Cartan elements for e.g. Lie algebras, and the idea of this tiny course is now to generalize everything what we've seen to L-infinity algebras. L-infinity algebras, I think the definition was the first definition you've seen. Yeah, so the deal always is you can always make out of an infinity algebra, you can out of an infinity algebra you can always make a DG Lie algebra. This is what John mentioned yesterday, roughly speaking. You can blow it up to a really, really big infinite dimensional space, and then you get rid of higher brackets. But the deal is that your vector space increases a lot. So just keep in mind you can always go to DG Lie algebras, but sometimes it's really easier to work with the L-infinity algebra itself. Okay, so since the definition was not present yet, we take and go back to your notes. This is the first definition what we've seen. This is an L-infinity algebra. An L-infinity 1 algebra, this is because we wanted to get rid of the signs and the issues. So we call this element is called Maurer-Cartan element if the Maurer-Cartan equation of this element vanishes, and this is defined to be so go back to DG Lie algebras. What you have here is that the higher brackets beside the differential in the bracket vanishes, and you really recover the Maurer-Cartan equation. Okay. I always will not comment a lot, but just to let you know, when I write this one here, so who can think of what I mean with this funny exclamation mark? So we didn't talk about topology, but here is an infinite sum. Okay, so just be careful. Sometimes it exists, otherwise it doesn't exist. We don't care at the moment because we anyway will tensor at a certain point with an Artinian ring, and then everything becomes a sum. Okay, what you can do with this Maurer-Cartan elements, you can twist the L-infinity algebra. This is actually a construction you might have seen already for DG Lie algebras. So what you do is you define a new map, which I fill in the first k arguments with the Maurer-Cartan element. And here there should be, this is stupid, sorry. This is k plus I, and here you have I times. Okay, now it's correct. So you fill in the first arguments with the Maurer-Cartan element, and the rest you keep with the original structure, and the lemma says now okay, we will not need the full L-infinity algebra for the definition of equivalences, but what we will need is the new differential. So just to recall, the differential was the first structure map, so if k equals 1. Okay, the proof of this It's an exercise. And just to let you know, this is rather annoying. So it can be done with elementary techniques, but it's really a computation which, if you use these techniques I just showed you, is kind of long. Yes?
We still add the infinite submission.
Sorry, I didn't know.
We still add the infinite submission.
Yeah, exactly. This is what my next point was with my red stuff. Again, convergence issues, just take care in your special situation. Okay, so now what was missing? So what was the idea of a deformation functor? The deformation functor was, we had the Maurer-Cartan functor, which we basically have now. We know what is a Maurer-Cartan element, and we had an equivalence. So the idea was that the zeroth component, or in my case the -1 component, because I shifted, acts like a group on the Maurer-Cartan elements. But this is not the case anymore, because we have these higher brackets. Okay? So I formulated the equivalence now as the way I see it, and this will be a bit different from John, but John will explain you at a certain point that everything is equivalent, and this is exactly the right notion. Okay, so we take two Maurer-Cartan elements from an L-infinity algebra, so they fulfill this equation here, and we say and this is a 1. By 1 are gauge equivalent. Depends on the nodes you're looking it up. Can also be homotopic. If there exists a path of Maurer-Cartan elements, because we are still algebraic, just polynomials in S. Here is S is just a polynomial variable, such that plus an element in the -1. This is how the -1 enters now the game, such that we have two conditions. So the first you can guess. The first is, if I evaluate at 0, if I evaluate at 1, you get back the one you started with. So okay. And the second one is an ODE now. Okay? So let's argue like this. Exercise. Check that this is gauge in EGLAs. You should hurry up because I think John will explain this today or tomorrow. The idea is, this you will see later, because now we don't see anything. We don't have any arguments why this ODE should exist or it has a solution. If the solution exists, it's unique. But later you will see that actually in some situations we can guarantee that there is a unique solution, and then we say, how does an element in here act on a Maurer-Cartan element? We solve this equation, and then we evaluate it 1. Okay? Okay. So, as I promised, we come back to deformation theory. So keep this in mind, what we can do, Maurer-Cartan element, twisting, equivalence. And now, let us, one thing I forgot. Basically, I'm here to post exercises today. So, this equation here can be formulated in a more compact way, but I decided to present it in this way for reasons. So, you take the L-infinity algebra and you see the polynomial in S and ds. Okay? This is a commutative graded algebra. And we saw yesterday that if we tensorize something with a commutative algebra, differential algebra, what we get is a new L-infinity algebra. We see it with Maurer-Cartan element, with Dirichlet algebras, but it works the same for L-infinity algebras. And the idea is now that this is a Maurer-Cartan element in this new extended L-infinity algebra. Okay, I always forget the signs. There are also different conventions, so there exists a sign such that this is correct. Okay, so now we come back to deformation theory. So what was always the ingredient in deformation theory? We had a local Artinian K-algebra, or as you like, a local complete, like this. Noetherian. But for us, this will not make a difference. There will be just some arguments I will write in blue, which you have to apply in order to get the results I will present you for this Noetherian K-algebras. Okay, so we do exactly the same as for Dirichlet algebras. So what we do is we tensorize with the maximal ideal. And the only thing what we can do is basically just say we apply these factors and tensorize and multiply here. Okay. Probably you should keep this formula in mind. This works exactly the same if you replace local Artinian with Dirichlet local Dirichlet Artinian, or in some order it works. But you have to apply this Kosul sign rule. So every time you switch something, there has to appear a sign here. This will give you exactly the same. You have exactly the same formula. And the idea is now that I think John wrote it like this. This, together with this new structure maps, which are in the end the old structure maps, this is an L-infinity 1 algebra. Okay? So, what we have to check now, the input is now, we can obviously take just this definition and say, okay, what is the deformation functor for a given L-infinity algebra? We take the Maurer-Cartan elements and we use this equivalence. But now we should check at least a bit that we can act and that this equivalence is not trivial. And there is a nice theorem, or lemma, let's say. Probably a tiny remark. So the structures become 0, and now I said that every time I write blue, I refer to the complete notarian, and here I write small. So in one case, the Maurer-Cartan equation is actually the sum, and in the other case, it's a converging sum. Okay? Converging in this filtration topology. Okay. So let us check now. What we can do with this new L-infinity algebra, where we know now a bit more because it has nice Maurer-Cartan equation. And the lemma is the following. We have and we take an arbitrary element gamma s in so this is exactly the equation we had here. And the lemma says as a unique solution. Okay, somebody has an idea? I think if I drop the line how to prove it, this is the, I think, only proof I more or less completely do. Somebody has an idea how to do this. Now you have to go far back because this is actually calculus 1. Let me clean the blackboard. What do I need? Okay. So the idea is now that there is something which you probably already forgot. This is called this iteration of Picard. So you can write it down and try how it works, if it works. And in fact, it does. So what you do is you define this sequence, and it's now clear that if we have a fixed point of the sequence, so if this converges to a fixed point, then it is a solution here. Just deriving everything and you will see. Okay, now we have to make sure it converges. The first point is, I basically give you an idea how to prove it. The difference is in okay. So if you just go far enough, then the difference is vanishing, it becomes stationary, and you solve the equation. This you can really show by elementary arguments and using this definition of the sequence. Okay? And keep in mind that both of these elements here are in this tensorized with the maximal ideal. Okay, the second point is that if pi s and pi hat are solutions, then from pi s minus pi s hat is in, so this, it follows that the difference is actually, sorry. This is the part of the proof. If you show this, then what you show is that actually they coexist. Because at a certain point, it will be in g times 0. Okay, so these are the first, these are the two stuff which you can show as an exercise, but basically you just have to write it down and you have to count how often you multiply in MA. Okay, so what probably you should use a different color. What follows now is that here I write it like this. It's a solution. And from this here is unique. Okay? And if I have to use the blue one, this holds true as well. Then it doesn't become stationary because there's a 0 here, but it converges. Okay? The same here. The difference becomes arbitrarily small, so it has to be the same. Okay. Did somebody see what I forgot here? Now we found a curve fulfilling almost everything to be an equivalence of Maurer-Cartan elements. But what we didn't check is the following. The Maurer-Cartan equation stays 0. Yeah?
So I'm a bit confused. Isn't differentiating by s just defined by sort of dividing by k degree k and sort of shifting the unit one over?
Wait a second, sorry, I didn't understand.
So you have this d over ds operator.
Yes.
So that I assume that's just defined sort of on something tensor s to the power I by sort of dividing by I.
Exactly.
So then sort of the bottom equation, you don't need to iterate, right? You can just sort of read off the coefficients from the bottom equation.
But I have already here a polynomial. So you can, I mean, you can iterate it exactly, but this is exactly how you iterate it.
Why do you need, I still don't get why you need to iterate, because sort of the thing on the right, that also depends on
S, yeah, exactly.
IS.
Yeah, exactly.
Okay, sorry.
Yes. Yeah.
Thank you.
I mean, the point is, as you said, you integrate everything,
Yeah.
but this is exactly how you do it.
Yeah, okay, and then you have to.
Yeah. Okay.
Thank you.
Yeah. Okay, so the last thing we have to check is that this curve stays, if we start with the Maurer-Cartan element, stays a Maurer-Cartan element for every S. And this, also I'm just saying how to do it, so in principle you can do it then, is show that the easiest way I found is you derive, so of course this is on n, derive at the origin, and then you see that every derivative vanishes, but we are in polynomials, or if we use this Noetherian, this complete Noetherian, then we are in somehow formal power series, but still still you can evaluate them, so just a subspace of the power series. But anyway, in both cases, if all of the derivatives at one point vanish, you're done. Okay. So basically what we've shown now is we have a Maurer-Cartan element, we take a path, we can also take a constant path that, sorry, here I forgot this one here. So what we have is that we can act with the degree -1, or if you go back to DG Lie algebras, in the degree 0, you can act on Maurer-Cartan elements. And so we can define a deformation factor now. So as we did, as Severin showed you and as John showed you. So the idea is now, you divide out by this equivalence relation. Just to be sure, this is some technicality. Good color for that. This might not be an equivalence relation. The idea is how to glue polynomials. It's not really possible, but there is a way to do it. But if you don't trust me, we take the transitive closure. Okay? So half an hour is over, and what we did is we just did everything which you probably knew already for L-infinity algebras instead of DG Lie algebras. It's a bit more technical because this is not really a group. Probably John will prove me different or not. This we will see. Okay, so it's just becoming a bit more technical, but the outcome is exactly the same. And now, what we still have to show is that this is actually a functor, right? We just have what we do with one Artinian ring or Noetherian, complete Noetherian K-algebra. So what we do now is we do exactly the same as in DGLA. If we have a morphism from A to B, then we just apply it to the second factor, and you have to believe me that this actually is a deformation functor in this set. Okay? So I write a note just like for DG Lie algebras, we can define 4 induces a map Okay, just apply to the second factor. You can check that it's compatible with the equivalence and the Maurer-Cartan equation. And it's compatible with the equivalence because we have a unique solution. And if we apply, we can provide a solution so we know it's a unique solution. Okay, questions so far? I know I was a bit quick probably. So I clean the blackboard, and this is where you have time to probably read what I wrote down and ask questions. Okay, no questions? Yes.
So, any of these changes if I take not Artinian algebra but DG Artinian algebra?
I mean, I think you just have to pay attention with the signs.
That's the same.
It's the same, yeah. I think John has a very more beautiful way, a more abstract way, a more beautiful way to define this deformation function for infinity algebras. This is really more down to earth.
So if you have an algebra tensor with the DG Artinian algebra, you've got another alternative.
Exactly, yeah.
So
this applies exactly in this.
and it's going to so you don't stop converge as well.
Exactly, this is what I meant. You have to pay attention with the signs. This is the you have to replace this, what John called tot.
Okay.
Okay? And then you're it's exactly the same. Okay, so there's still the word exercise written. So the last thing I want to say today is actually what we did is we took the categories of Artinian, local Artinian K algebras, and we defined via a DG Lie algebra or an L-infinity algebra, we defined a deformation functor into sets. So now the question is obviously what happens when I change G? So what are the kind of changes are allowed to G? And if I change G, how does the deformation functor change? Okay? So what do we need in order to change G? We need to know what are morphisms in the category of L-infinity algebras. And this is, as everything in L-infinity algebras, rather annoying. There's a more conceptual way, but you will see why I say it's annoying. Actually, Severin didn't want to do it because he said it's so annoying. Okay. We take two L-infinity 1 algebras. And a sequence of maps by n is called L-infinity 1 algebra morphism. Okay, just think back or look back in your notes. What was the definition? One of the definition was there has to appear a sign somewhere. We're not here for fun. So if you have any order here, you can bring it back into in this order, but you get a sign, and this is the Kosul sign, which Severin introduced. That you just, if you flip two elements, then you get a sign depending on the degree. Okay, and now the compatibility with the structure maps of the infinity algebra. This is two sums. How did you call the shuffles? Something like I use this. Is it okay? I cannot do this frag what 7 can. And what you have here and this is the same as there is a sign missing. This is the same as this one here, and there should be a factorial and a sign. And of course, there should be second sum. I forgot. And I write just here
It's a sum of I1 to IR.
Ah, yeah, sorry. This is n. Sorry. Exactly. So you have a huge sum. You have something you don't want to check for anything. But at least it's once on the blackboard. But it seems like this is the correct notion one should use. Keep in mind that if you say I have two DG Lie algebras and I consider L infinity morphisms between them, they don't boil down to just DG Lie algebra morphisms. You can always have this higher maps. Higher maps, I mean, I refer always to maps with more than one entry. So you can check in like the first some orders to get a feeling for that. But so the idea is the second structure map, if you just consider DG Lie algebras, the second structure maps measuring the failure of the first one to be a Lie algebra morphism. Okay? So there is something like this. I write it here. If you have a DG Lie algebra, then you have something like exactly. And since I don't remember any sign, I put something like this. So this is what I mean is the second map measures the failure of being. Okay, you can make this as an exercise, and the higher ones, they become very, very easily non-tractable anymore. Okay, so what can we do with them? Or why did I tell you that this is the correct notion? So we are interested in Maurer-Cartan elements, so it would be nice if we can induce by an L infinity morphism or an L infinity 1 morphism a map between Maurer-Cartan elements. This is the first thing we should check if we want to follow this philosophy of deformation functors, Maurer-Cartan modulo equivalence. So let me check. So we have just a list of stuff which will happen, which is true for these morphisms. The first one is very important. So the first structure map is compatible with the differential. It doesn't matter what the higher ones are. It's a cochain map. And what is happening is how we say phi is a quiz, so quasi-isomorphism of L-infinity algebras if phi 1 is a quiz of complexes. Just remember the first structure map in an L-infinity algebra, this is what Severin showed, and there was also an exercise for that, is always a differential. And what we are saying is this one is a quasi-isomorphism of L-infinity algebras if the first one is a quasi-isomorphism of complexes. So being a quasi-isomorphism really doesn't matter about the higher maps, we just have to know that they exist and make everything into an L-infinity algebra. Okay. This will become more important tomorrow. Just keep this in the back of your head, because Severin shows cool stuff about L-infinity algebras and minimal models. Okay, so we take a Maurer-Cartan element in one of the L-infinity algebras, and what we do now is we define a map, probably I call something like f hat, 1 over k faculty, and we feed in the Maurer-Cartan element k times, and we sum everything up. So again, be careful here. If we have infinitely many higher structure maps, there might be convergence issues. So this is in our Cartan element. Okay, so you always have a map induced by an L-infinity morphism from Maurer-Cartan elements to Maurer-Cartan elements. Yeah?
Sorry, it's f phi.
Ah, yeah, sorry. Sorry. Yes. Correct. Okay, so you can feed in k times. You get a Maurer-Cartan element back. This is again, you can check it, but it's rather annoying. So you probably need 2 more minutes or 3 more minutes. So what I do now is actually what you can think of now. I have an equivalence of Maurer-Cartan elements, which was this funny solution of a ODE and had a unique solution. So now we have to produce out of this pair, which was this pi s and gamma s, a new Maurer-Cartan element, a new curve of Maurer-Cartan element fulfilling an equation like this, this ordinary differential equation, and this is also possible by, so I just say if pi 0 is equivalent to pi 1 via pi s and gamma s, so this was exactly the two stuffs we need, then pi hat of pi 0 is equivalent to via this one here, and now we need the other map, and this is gamma hat S, and we define it as K faculty, and then okay. So you can also check that this element together with this element fulfills this ODE. We know that we have a unique solution. So this has to be the solution, or this has to be the solution, and then you can see that if they are equivalent, then they have to be equivalent by giving exactly the path with the help of the infinity morphism. Okay. And as you might expect, there is this one here. Again, we have an infinite sum and we don't have the product. Okay. I'm a bit over time already. So let me just write down one paragraph and then you can ask me in the break if everything is not clear, and probably you have to ask me anything because a lot was not clear. So, deformation theory. So, if we, let's say, switch on the Artinian ring, then none of these exclamation marks are an issue anymore. So, and why? Yeah, since is 0 at a certain point. And these are defined as you might expect. Okay, so we apply to the x's and multiply the a's. So, and then you can see why this is 0 at a certain point or small. Okay, so one diagram and you can have coffee. Let me put it here. So the idea is now that if we have two L-infinity morphisms, we can compare the deformation functors of the corresponding L-infinity algebras. And we have already a morphism from Artinian rings. And the only thing what I will do now is I will say the following. We have def B of A. And with this lemma here together, we have that phi AK goes to the deformation functor here. Okay? This is basically saying we have Maurer-Cartan elements and we can move them to the other L-infinity algebra, and we also have a morphism which moves the equivalence to the other algebra. So we in particular have a morphism from the deformation functors. Then if we have a morphism of Artinian rings or local Noetherian K-algebras, then we get this deformation functor. We again have Let's do like this. We can have this one here. And on the other side, we also have this, right? We have okay, and I'm claiming now that this is commuting. And this says nothing else than an L-infinity algebra morphism gives you a natural transformation of their deformation functors. Okay. My last thing, but to check this is actually really rather easy. The idea is really that the phi, the small phi and the big phi, they act on different tensor factors. So obviously they commute. That's the whole idea about this proof. We've seen this phi just acts on the MA and MB, and this big phi just acts on the higher maps in front. Okay? So I hope, I know I was very fast, and just relax a bit, look in your notes, and ask me questions during the coffee break. And I think we